All right, so today we're going to talk about solutions and figuring out molarities through use of moles per liter equations through dimensional analysis, and also how to make solutions from solids and then through dilutions. You can see here on the table I have all these different flasks, and they're kind of all pictured there as well. They're ranging from this incredibly adorable 10 ml flask. It's the cutest thing I've ever seen in my life. I kind of want to make earrings out of it. It's so cute. Then we got the 50 ml, we've got a 100 ml, we got a 250, a 500 ml, and then we have a liter flask, and then 2 liters. So the reason I'm showing you these is because when we talk about molarity, there's going to be oftentimes you're going to have to either make solutions in AP, or you're going to have to tell me how you're going to make solutions. And it's with these flasks that we bring all our solutions to a specific volume. And all of these have one line on them, which is the volume intended to be the volume of the volumetric. So these are called volumetric flasks. You're welcome to come up after lecture and look at them if you would like to. Don't steal my 10, because it's so cute. All right. So in this first problem, we're tasked to calculate the molarity of a solution by putting 0.875 moles of NaCl in 1 liter. And who remembers what molarity actually is? Okay, let's be more specific. Moles of what per liter of what? Solute, moles of solute over liters of, it's solution, not solvent. And I want to talk about the difference between those two. It's different to say moles of solute per liter of solvent, and that's not exactly correct. So when we make a solution, we're going to place, I'm going to use this little guy right here. He looks like it's the 500 ml flask. We're going to place a certain amount of solute into the flask, okay? And then we're going to fill it to the mark with water. That, by definition, is 500 mils of solution because it contains both. That is different than taking 500 mils of water and adding it to a certain number of moles. Do you see the difference? Because this might end up, because of the amount of space or whatever these moles take up, this could be ending up to be more than 500 mils of solution. All right? So by definition, it has to be total liters of the full solution to be a molar solution. Okay? So if we're going to calculate the molarity, we're going to put, and I want you to save a good chunk of this page for a question we're going to add. So save this space here. We're going to add a question to it in your notes later. So kind of keep your writing up top. Calculate the molarity. If we have 0.875 moles of NaCl in 1 liter, what's the molarity? Please don't use your calculator. 0.875. Now, you're in big kid chemistry now. You can use a capital M, it would be accepted. However, we're going to be doing a lot of problem solving with molarity. So having those units separate and cancelable make it easier for you. So I want you to write moles per liter, okay, as your units. Now, if we have 500 mils, we're putting the same number of moles in less volume. What is 500 mils in liters? 0.500. So are we going to get more or less concentrated? We cut down on the solvent. More concentrated. So it's actually going to double that value, isn't it? And what is the value to 3 sig figs? 1.75 moles per liter. So I want to keep 3 sig figs. Go ahead and make that a significant 0 and that a significant 0 and do 0.00 on your things. Let's keep it at 3. Okay. So now we're really going to concentrate it. We're going to put that 0.875 moles, into how many liters if it's 100 mils? 0.100 liters. So what's my concentration there? 3 sig figs, 8.75. All right. And then we're going to make 6 liters, 0.875 moles divided by 6.00 liters. How many moles per liter is that? 0.1 what? 0.146 moles per liter. So that's really diluted compared to whatever. So when we make up solutions, when I'm making stuff up for the lab, I calculate, okay, I need 3.5 liters for all my classes, right? Well, I don't really have a 3.5 volumetric. I could sit there and do 3 of these and 1 500 and all that kind of mess, but what I probably will end up doing, this is a 2 liter, I'll probably end up making 4 liters. So you always are making your solutions with these available pieces of equipment in mind. You don't want to make 375 mils of something because we can't get to the accuracy that a volumetric can get to it if we don't have one that volume. Okay? All right. So any questions on how to do the formula way? We're going to do some dimensional analysis with this now when we actually prepare some solutions. So how would you prepare 500 mils of 0.05 molar copper 2 nitrate? And I want you to note that this is solid. So if that's solid, what are we going to need to figure out to know how much we're going to make? That is 500 mils. So here's a 500 milliliter flask. Okay. I need to know how much copper solid I put in here. So what am I going to end up calculating? Moles. Is moles a useful unit for me in the lab? Do I have a mole scale in the back? No. If I need to know how to make it, what do I probably need to figure out? Yeah, I'm going to need to figure out how many grams of copper nitrate I put in this flask. Okay? So we're going to start out, and we can do dimensional analysis here pretty simply. I can start out with my, really doesn't matter. We can start out with 500 mils if we want. Is that a useful number in molarity world? What should I convert that to? Liters. So for every, what? 1 liter I have 1,000 mils. All right, so now I'm in liters. So the molarity, if I just go ahead and put this in my dimensional analysis, which is kind of cool, I can write 0.0500. What are the units on that again? Nope, moles per liter. So what have I calculated there? What do I have right now if I stop this dimensional analysis? I have moles. Liters cancel, mils cancel. So right now I just have moles of my copper 2 nitrate. But what did we say we needed to get? Grams. So for every 1 mole of CuNO32, what do I have? Come on, guys. 87? That doesn't sound 187.63. All right. So when I multiply all of that out to 3 sig figs, well, it's actually, yeah, 3 sig figs, how many grams will I need to weigh out? 4.67 grams. Is that right? 69? 4.69 grams. I'm going to weigh out 4.69 grams. And so now I want to write how we would make it. We're going to weigh out, and this is the important part, how to make it. I'm holding you responsible for knowing how to make it, not just to do the math. Weigh out 4.69 grams of copper 2 nitrate. Place in a, what kind of flask? How big of a flask? A 500 mil volumetric. Then what do? Add water, fill with water to the line. The fancy word for that is QS. That actually has its Latin, but in English we say that's quantity sufficient. If you say I'm going to QS it, it means you're filling it to the line. That's what we do. We weigh out our stuff, carefully place it in here so not to lose any, and then we fill it up with water to the line. And then one other step that's a little bit different this year, since you guys are actually going to be making them, I want you to add invert to mix. Because what you then do, you got to mix it, so you'll have a cap of some sort like this guy here. You're going to put the cap on, and then you're going to invert to mix it up. Okay? So that's how you would make that solution. Any questions on how to make it? No? All right, let's do the next one. Calculate the volume of 0.5 molar copper 2 nitrate needed to prepare 250 mils of a 0.04 molar copper 2 nitrate solution. Here's 250 mils. What's different about this problem, though? We have two solutions, but what are we doing? Let's look at the concentrations. We're making 0.04 from a 0.5. What are we doing to that solution? We're diluting it, all right? So whenever you have a stock solution of a higher concentration and you're making something of a lesser concentration, you have to dilute. Anyone remember the dilution formula? MV. Y'all remember that? So if you don't, jot it down. M1V1 equals M2V2. So whenever you're going from liquid to liquid, more concentrated to less concentrated, you can use your dilution formula. So what we do here, I like the M1V1 to be the stock solution, stock being the more concentrated one, and then that's just how I set it up. It's not wrong if you do it the other way. But I know that my stock solution is 0.500 molar. I want to know how much volume of that I need. What is the molarity of my wanted dilute solution? 0.0400. And then 250 mils is the volume. Can I put mils there? Sure I can. Anyone, what's the difference? Why can I put mils here? What? Then your answer will come out in mils. This is just a proportion. This is not a unit cancellation situation. But whatever volume I put here is the unit of volume I'm going to get out here. Why do mils not work in the previous problem? We didn't leave them mils. Exactly, because mathematically that molarity we were using to calculate was actually in liters, so we had to convert for unit cancellation. Okay? But in this one, we're going to figure out what is the volume we need. So it's 0.04 times 250 divided by 0.5. 20. How do I do 20 as 3 sig figs? It looks like it's going to be 2 sig figs. How do I do 20 as 2 sig figs? Decimal, or you can put a bar over it, so 20 mils. All right, so now that we know how much stock we need, how are we going to make this? We're going to put 20 mils of what? 0.5 molar copper 2 nitrate into what? Into a what am I making?
You're trying to make the 250 milliliters of 0.0.
Right. So what am I going to put that 20 mils of stock in? The 250 mil flask. Into a 250 mil flask. And then what do I do? Fill to the line with water. And then what do we do to mix it? Invert to mix. So that's the level of detail you guys have to have on your problems when I'm asking you how to make something. If I just want to know an amount, I would say how much would be required. This problem actually could have ended here because I said calculate the volume and that's all I said. But if I ask you how to make it, you would have to say the rest, okay? All right, this is a good problem, this next one. This is a little bit of an advanced problem. Determine the molarity of total ions in solution prepared by dissolving 9.82 grams of copper-2 chloride in enough water to make 600 mils of solution. So that's our first thing. We want total ions. And then it says, what is the molarity of just the chloride ions? So when you're asked, this is a very big AP kind of problem. It shows up a lot. They want to know concentration of ions, and you all freak out. Oh, it's so hard. No, it's not. You find the concentration of your substance first, and then we can move from there and find the concentrations of all the sorts of different ions. So let's not panic. The first step, I just want you to find the concentration. And if I write this, that's concentration. If you see anything in these brackets, find the concentration of just the CuCl2 first. Let's do that first, then we'll talk about ions and stuff. So, how do I get to concentration of just the CuCl2 in molarity? What do I start with? Yep, we got 9.82 grams of CuCl2. I want to convert that to moles. So for every 1 mole, how many grams do I have? Thank you, 134.45 grams. All right, so now my grams cancel. I'm in moles. How can I convert this to molarity? Moles over liters. Here's the beauty about dimensional analysis. I can put the 0.600, you see how that's 600 mils? I can put the 0.600 liters right there and be done because moles per liter are the units of molarity. Don't be afraid to have something here with nothing on top. It doesn't matter. Mathematically, the units are going to work out appropriately, okay? So, what would be then our concentration of CuCl2? 0.122 moles per liter. Okay, so now let's look at the question. The question saying calculate the molarity of total ions. Well, if I know I have 0.122 moles of just CuCl2 per liter, I can relate that to anything associated with CuCl2. In 1 CuCl2 mole, if you put it in, they dissolve. How many ions do you get per mole? 2. So 3. If I dissolve this, how many ions do I get? A copper ion and 2 chlorines, right? So for every 1 mole of CuCl2, I have 3 ions. And that number will be my ions, total ions per liter. Get it? All right, so 0.366, yeah? Moles of ions per liter. So that's answering the first question. What was the next question asking? Molarity of just chloride. How's that going to be different? Exactly. I still have 0.122 moles of the CuCl2. Well, for every 1 mole of that, I only have 2 Cl minus ions. So my number is different, but the process is the same. Is everybody with me? Y'all look a little scared. It's just like what we did with going from moles to atoms. I'm sorry, from molecules to atoms. You just took how many pieces were in that thingy and converted it to atoms. How many in the subscript in the number, how many parts there were gave you atoms. So we get 0.244 here. This is moles. And you're going to see a lot of this. In that Zoom doll textbook, most of the problems, most of your homework problems are going to be ion calculations. Okay? Don't panic. It's not hard. It's just an extra step. So focus on molarity of the initial undissociated stuff, and then you can get the rest. Okay. So this next problem, I want you to go back and put on put this problem on the free space that I told you to keep, because this is in regards to the lab we're starting on Friday. And this calculation you're going to have to do on Friday with your partner, because it's going to be a partner pre-lab in class on Friday first, where you have to do some dilutions, and then you have to figure out how much nitric acid you need to dissolve your bullet. So here's the situation. You're going to each get a bullet casing. There's no ammunition in it. It's just a bullet casing. Does anyone know what those are made of? Brass, yeah. So your job will be to figure out what manufacturer made your bullet based on the percent of copper in that brass. Different manufacturers have different percents of copper. So the first step of the whole process is to dissolve your bullet, or the casing, in nitric acid. It is a super duper cool looking reaction, and it's giving off NO2, which is toxic, but that's cool. It's under the fume hood. You'll be fine. And it makes a really deep blue copper 2 solution. So the brass containing the copper, we're going to dissolve basically the whole thing and make it, I call it bullet juice. It's a solution that's just going to be, your bullet is totally dissolved. So part of your job will be to figure out, okay, if I know my bullet casing weighs this much, and pretending it's 100% copper, how much would I need? How much of that 16 molar nitric acid would I need to react it? So I'm making up a number here. Your casing is going to weigh a whole heck of a lot more, but I just want to go through the calculation and make sure you understand it. So Friday, you're going to be on top of it. So if our casing, or if our copper is 0.345 grams, how much nitric acid? That's liquid. 16 molar means it's a solution. So I want to know how many mils of this stuff I have to add to react with 0.345 grams of copper. And I know it's 16 molar. So in order to get milliliters from molarity, what piece of information do I need? In order to get milliliters from molarity, what do I need? Moles. Well, yeah, liters, but we still need to find liters. What would I need to find liters? Moles. Don't I need moles? Once I have moles, I can find liters, and then I can find milliliters. So how do I get moles? Stoichiometry, right? Mole bridge. So I'm going to start with my given, 0.345 grams of copper. What do I have to do to get on the mole bridge? Y'all are really quiet today. I'm tired too. Let's go. Convert to moles. For every 1 mole of copper I have 63.5 grams. So how many moles of copper do I have? Oh, we don't need to do it separate. Now we're in moles of copper. What can we do? Right, mole bridge. For every 1 mole of copper I have 4 moles of nitric acid. So what are the moles of nitric acid? You know what? Let's keep going with our dimensional analysis now that I think about it. Do I really need to even do this math? Because what do I have right now if I were to stop? Moles of nitric acid. How do I get molarity of, I've got molarity of nitric acid, right? Molarity is 16 moles per liter. Did you see what I did there? So now the moles cancel, and I'm going to get liters as an answer. So you don't have to stop and find each of those things. You can do it in all one-dimensional analysis. So what is my number of liters? Just give me 2 sig figs because I'm being sloppy here. .0014. Does everyone agree with that number? .0014 liters. Is that a useful number for me? In the lab? No. What should I do? Make it milliliters, 1, 2, 3. So it's 1.4 milliliters. That's a little bit more usable of a number, right? Is that right? First period got totally a totally different answer. 1, 2, 3. Is this wrong? So what's wrong? You're looking at me like I'm doing something wrong. I could be, but oh, I'm basing it on 16 mils. 16 molar. 266. Okay. God, last period got like 0.0 something.
You can check it.
What?
Like you can reverse the thing and check
Yeah, no, I believe you guys, and I'm glad that we're getting it right on the video, but I don't know why last period we got 0.0 something, and I was thinking in my head, I was like, that doesn't make a lot of sense. Yeah, but, I mean, we have pipettes that can do that, so I'm going to go back and look at the notes from last period and see where we messed up. But anywho, I think this is the right answer. Okay, that makes sense. All right, so let's move on to a bit. This was technically the end of the lecture, but because it was so short, I want to kind of prep us for tomorrow, because tomorrow some of your heads might explode, and this will alleviate a little bit of the stress. So first, I'd like to say again, welcome to AP Chemistry and the need to memorize things. So solubility rules, which you were provided with in the past, you will not be provided with anymore. You have to know your solubility rules. I'm going to make these a lot prettier and simpler as we go through them. I just want to show you what you're presented with in most textbooks. You get all these crazy things, but I'm breaking it down to as simple as I can do. The first rule, most alkali metals are all what group? Group 1. So group 1 salts and ammonia salts are soluble. Always. Wake up, Jacob. Don't miss this. You're going to miss the good stuff. Go walk around if you need to. I want to combine that 1 and 4 because nitrate, don't worry about the chlorate, hypochlorate, or perchlorate, excuse me. I want to combine the always solubles together. Group 1 metals, ammonium, nitrates, and what is that? You know it. It's just rearranged. No, not cuckoo-cuckoo. It's something you know. No, it's a polyatomic you know. It's acetate, C2H3O2. It's just written the way it's structured. This is a structural representation of acetate. This is the acetate ion. So, group 1 metals, nitrates, ammoniums, and acetates are always soluble. That, my friends, is the Big Daddy rule. Big Daddy is in charge, and anytime there's those, they're going to supersede any other rule that might be out there. Here is Big Daddy. He's a pimp. He runs the place, all right? That's the Big Daddy rule. Now, cross out number 3 entirely because it's rare, and I'm just concerned that you know the main parts of this group. What group is this one? Cl, Br, and I are all in what family? They're all halogens, so I'm just going to write this as a halogen rule. This is a rule of halogens. All halogens are soluble except for silver, mercury, and lead. So I've made some mnemonics, and they suck, but it is what it is. And if you want to make new ones, you can, but no one's come up with new ones, and everyone's memorized these, so it's awesome. Halogens. You know, Hal is a name. Hal, halogens. Hal hugs Aggies pretty badly. Hal, all halogens are soluble except mercury, silver, and lead. Pretty badly is lead. All right? Hal's right here. Here's Hal. And he can't hug. He hugs pretty badly. That's an A&M helmet. That's Hal. So all halogens are soluble except, so the two, I'm about to show you another one of these. When you have the two Hal or Sol rules that I show you, These are the exceptions to solubility. They are insoluble. Everything is soluble but the things listed in the mnemonic. Okay? All right. The other rule is for sulfates. It's really important to remember that is sulfates, not sulfides. Later on, people see something with an S and think it's a sol. No, it has to be a sulfate. So sulfates are all soluble except for calcium, strontium, barium, silver, mercury, and lead. This is a good one. You guys are going to be so incredibly impressed. All right. Sol is also a name. Sol. Here we go. Can, bag, hags, pretty badly, in Sri Lanka and Argentina. Here's Sol. He's putting an old hag in a bag. See him? And I need like a sign, Sri Lanka, Argentina, that's where he does that. Again, they're horrible, but they work. And if you want something else, that's in your court. I'm giving you something. So sulfates. All sulfates are soluble except calcium, barium, mercury, lead, strontium, silver. I mean, yeah, and however, if you want to do it by patterns on the periodic table, go for it. I just have this ingrained in my brain. Okay, so now let's, and this last one, please don't memorize it. It's basically everything else. Everything else is insoluble unless it's connected to a big daddy, so you don't have to worry about it. Okay, so don't memorize that last one. That's ridiculous. But do you see how here it's a sulfide? That's not sulfate. So don't get this rule mixed up with sulfides. It's sulfates. Okay, so which of the following? I want to know why, if it's soluble or insoluble, and why. Silver nitrate. Soluble, why? Nitrate, soluble, because that's a big daddy rule. Soluble because of nitrate. Sodium chloride, you better say soluble. What makes it soluble? It's a group 1 salt, so it's soluble. But also, all halogens are soluble except for silver, mercury, or lead, and it doesn't fit in that category either, so it's soluble. Lead-2 bromide. It is not soluble or insoluble. Why? Just refer to a rule. I don't need you to explain the chemistry behind it. Halogen, bromide's a halogen. Hal hugs Aggies pretty badly. What's going on there? It's lead, right? It's the halogen connected to lead, so pretty badly. It's pretty bad. Ammonium hydroxide. Soluble, why? Big daddy ammonium. Barium sulfate. Insoluble. Why, Matt? Barium is an exception to our sulfate rule. Sol, can, bag, hags, bag. Bag. All right, I'm going to go back to calcium in a minute because we have to have a little chat about calcium hydroxide because unfortunately I put it there because I needed to remind me to talk to you about it. But lithium carbonate, that's soluble, big daddy group 1. Right? Now, other carbonates that aren't group 1 won't be soluble. So just tell yourself, if it's not one of the ones you know that always is or one that you know for sure, then you just say insoluble. Okay, calcium hydroxide. Here's the dealio. Based on these rules, this calcium hydroxide would be what? Is it a group 1? No. Here it says are all insoluble. So technically, this is insoluble, right? We also know this to be true because of what we talked about with bases yesterday. Strong bases dissociate 100%, right? Right? And is that a strong base based on our rules? No, our strong bases were group 1 hydroxides and the bottom 2 of group 2. Here's the thing about calcium hydroxide. Calcium hydroxide is a weak base, so it's not truly 100% insoluble. It does break up some. So on the AP, they might have you assume it is soluble. I'm never going to ask you a question, is calcium hydroxide soluble or not, because it's too much of a gray area. I just want you to know that sometimes they'll say, oh, a 0.1 molar solution of calcium hydroxide, and you're going to be like, I thought that was insoluble. How can you make a solution? You can at low concentrations, really low concentrations. So this is actually, and if you want to make a note, I don't want you to stress about it because I'm not going to ask you specifically about it, but calcium hydroxide is considered strong, actually breaks up at low concentrations. So just know you might see some contradictions with that one. Specifically just him, that one, that's it, nothing else. Everything else is pretty straightforward. Okay, so now you have the rest of the period, a good 12 minutes or so to work on homework 12A. I mean 12, I wish. 2A, and you can probably knock it out before we leave.